Chapter 4, Hermitian and Symmetric Matrices. We have covered a part of section 4.1 up to theorem 4.1.6. So, yeah, we will briefly go through it once again. Then we will start from theorem 4.1.7. 4.1.7. Okay. 뭐지? 이건가? Okay, yeah. Okay, chapter 4. Yeah, the first part of chapter 4 was a motivation of studying Hermitian and real symmetric matrices, and Hessian matrix was a major motivation for studying Hermitian matrix, and quadratic form is also a major part of the research on Hermitian matrix, because the research on A and the research on the symmetric matrix 1/2 of A plus A transpose are giving the same information for the quadratic forms. So we only need to study this symmetric matrix instead of A when we deal with the quadratic forms. That's why we only care about the symmetric matrices in the research of quadratic form. Okay, and second order linear partial differential operator was also a part of the Hermitian matrix, and the undirected graph is also Hermitian matrix, and here by linear form also are using the same Hermitian matrix, and there are some variation of bilinear form which is called the SKKU linear, but still Hermitian matrix is enough to deal with those areas of research. And definition of Hermitian matrix, which is A star, the conjugate transpose is same as A, and it was given before, and also Q Hermitian, which also it was defined before as a conjugate transpose is same as minus A, and these are the facts on the Hermitian matrix, such as any matrix can be written as a Hermitian part and the skew Hermitian part, and many others. We covered it already, and this is the first theorem of chapter 4, which is a generalized form of what you have learned in the elementary linear algebra. The only difference thing is now we are using Hermitian and the skew Hermitian instead of symmetric and skew symmetric, because now we are dealing with a complex matrix, which is more general than the real matrix. But all these arguments are exactly same as what you have learned and studied for the real symmetric matrix in your elementary linear algebra class. And this is for the Hermitian, x star ax are real for every n-dimensional vector x, and all eigenvalues of A are real, and S star AS are Hermitian for every matrix S. Actually, one of your midterm exam is just a special case of this theorem. So you should be able to deal with it, because the proof was so simple, like you see here, and you have learned it already. But actually, it was a problem of elementary linear algebra level, not the graduate. Okay, and conjugate pair. Okay, and this was a fact that you used. If G plus W are real and G minus W is pure imaginary, then they are conjugate pair each other. So we use this fact in the proof. Okay. Yeah. Here the one fact is every matrix is similar to its transpose, but may not be similar to the conjugate transpose of A. Okay. This was the example. Okay. Yeah. This was the proof that we learned. The end. Okay. And you've learned this proof is very standard, very typical. And all the other parts are very trivial, and only proof with a significant contribution was the proof from part 2 to part 1. Okay? And this was the argument that we used, and I gave you some variation of this technique, because this is technique only it is you've seen this technique for the second time already in our class, and this was a similar technique that we used. And here what we used was the addition was a real number, and conjugate transpose of it is the imaginary. Addition of two numbers are real, and subtraction of two numbers are pure imaginary. That means they are conjugate transpose. That's the fact that we mentioned. And we use that fact to draw this matrix Hermitian. And yeah, we explained it in detail a week ago. And yeah, the others are just followed. It is followed directly. Okay, and yeah, this is another characterization of Hermitian matrix. If A is Hermitian, there is a unitary matrix that makes that matrix is similar to real diagonal matrix. So this is so Hermitian matrix is unitarily diagonalizable to a real matrix, real diagonal matrix. This is called the spectral theorem for Hermitian matrices, because all eigenvalues is Hermitian are reals, even though the matrix is complex. What that means is this is a Hermitian matrix, but the eigenvalues are all on the real line. You know, if it's a Hermitian matrix, eigenvalues are on this line, not the complex numbers. So there is a very strong characterization of the Hermitian matrix. Okay. And this, yeah, simultaneously diagonalizable if and only if it's a commuting family. Yeah, this is what we already seen in the previous chapter. When you have a commuting family, we can expect pretty much of the interesting fact that related to the simultaneously something. Okay. Next, here. Now we start. Okay. Previous up to the previous theorem that we had covered. Now we start. Now we start from here today. We start with Okay, theorem 4.1.7. The followings are equivalent. A is similar to A is similar to a Lear matrix. Lear matrix. If and only if A is similar to its conjugate transpose. Okay, we can prove from here to here, and then A can be written as H A star H inverse for some Hermitian matrix H, which is non-singular. Okay, we can prove from here to here, and then A can be written as the product of two Hermitian matrices. One of it is non-singular. Okay. Then A can be written as the product of two Hermitian matrices. This is trivial because it has a less condition, so that is true. Okay. Then we can show from the last part of this theorem to the first. Okay. Yeah, I will prove this. I will use this roof to show this theorem. This is a good characterization of the Hermitian matrix. Okay. Let's start. First part. A implies the B. Okay, A is similar to B, so there is a non-singular matrix S. That makes A is S inverse is equal to B. Okay, then but B is a Lear matrix. B is a Lear matrix, so B is always similar to the B transpose. So there exists a non-singular matrix T that makes B is equal to T inverse B transpose T. Okay, non-singular matrix S and T. Then, since B is a Lear matrix, so B transpose is same as B transpose conjugate, B star. So we can just write it. Okay. Then B star is same. It can since B is a SAS inverse, B is a SAS inverse. So we can write. We can replace it. Then the conjugate transpose of SAS inverse can be written in this way. Okay, then we can just rewrite it in this way. Here, S and T are both non-singular, so S star T is also non-singular. What that means is A is similar to A star. So now we proved this part. Okay. Second, I want to show B implies A first. Okay. This is the reason that I show this one first is when I show from E to A, this is the hard. The others are very easy, and this is the hard part. When I show it, I will use this routine first as a part of that proof, and then in the other case, I can go directly from E to A. So yeah, I will have the fact equivalent condition of A and B statement first. Okay, I will start. This is a Jordan canonical form. Okay. Transpose and star. Okay, A is similar to A star. Now we show B implies A. A is similar to A star, so yeah, it's always A is similar to A transpose, and A is similar to A star, which was the condition. So we know the Jordan canonical form of A transpose same as Jordan canonical form of A, which is same as Jordan canonical form of A star. Okay. Anyway, since we do have that, so we can take the transpose of this similarity relations both. Okay. So we do have transpose of A transpose is similar to the transpose of A star. Okay, what implies the transpose of A same as A, and the transpose of A star is conjugate of A. So what that means is we have A is similar to A conjugate means if we have an eigenvalue lambda here, then there is a corresponding eigenvalue lambda bar. If we have one, then there is the conjugate of it. If you have a real number, real eigenvalue, then there's no problem. But if you have a complex, then you should have a complex conjugate of that eigenvalue as its eigenvalue as well. Okay, so B. So B is if B is a real matrix of n by n size, then Jordan block corresponding to lambda, we should have a same Jordan block corresponding to lambda bar. Okay. So this matrix CAB is something like CA here B minus B. So this is the notation that we use for this. So if lambda is a real matrix, then we don't care. We just lambda and do something. It's lambda. Then if it's a lambda, then we just if I all real, then we don't have to worry about it. When these are the complex, then we should have a conjugate transpose of it. When they are if we have something like lambda bar, then we can just write it in this way. This is similar to this matrix, so we don't have to care. But when we don't have enough linearly independent eigenvectors, then we should have a Jordan canonical form of this type. Okay? Jordan canonical form. Yeah. When we have a Jordan canonical form of this form, this is similar to this block matrix of A B minus B A like this. Okay, yeah, this is just the background of for that we will use in our argument. So anyway, yeah, we know that each eigenvalue appears as a conjugate pair, and lambda and lambda bar has the same Jordan blocks. Okay, so we can think. Okay, we can think the matrix A is similar to a real matrix because this matrix A has is similar to a matrix of this type of blocks. We have by the Ch4 theorem. Ch4 theorem, we have lambdas and like this, isn't it? So by Jordan canonical form, we have Jordan blocks, and lambda and lambda bar. If those are all diagonals, then we have a simpler form of this, which is just real numbers. If we have a Jordan blocks like this, then we have this type of blocks. So anyway, all we have to think was the case that lambda is here and lambda bar is here, whether it's 0 or not. Then this, so this, from here we can find the similarity from here to this matrix. So in any case, this A matrix A is similar to a real matrix like this, and the block matrix with this type of the blocks, which is a real matrix. What that means is A is similar to a real matrix. This is the this shows if A is similar to A star, then A is similar to a real matrix. So now at least we have A and B are equivalent. This is all comes from the knowledge on the Jordan canonical form. And the only thing that you have to worry about is the conjugate pair of it. So the way of you dealing with that conjugate pair is this technique. This matrix, you can find the real matrix which is similar to that Jordan block. Okay? Okay. Next, B implies C. Now we have A similar to A star from here. So A is similar to A star, so there exists a non-singular matrix S, and we can find the alpha, which is the R e to the I theta, and then use this alpha, the scalar alpha, to multiply it on S to get a new matrix T. Then T inverse A T is also the A star because it's cancelled each other. So we have A T is equal to T A star. So if we just take a transpose, the conjugate transpose on both sides, then we have T star A star is equal to A T star. Okay, here A times A T plus T star is same as T plus T star times A star. Now, now T plus T star is Hermitian. So if it's a Hermitian, if we take a proper alpha to make this T matrix T non-singular, we can do it because choose alpha to make T non-singular. Okay. This is possible because T plus T star is non-singular if and only if and only non-singular. So multiply T inverse, then this I plus T inverse T star is non-singular. This is if and only statement. If it's non-singular, then this is non-singular. But as you see here, now we think the eigenvalue structure of this matrix. If this is a non-singular, then -1 is not an eigenvalue of T inverse T star. Okay? If not, then we have a diagonal. Diagonal entries are 0. Then if -1 is the eigenvalue of it, then definitely of this one, that definitely is going to be the singular matrix. So if it is non-singular, then -1 is not an eigenvalue of it. here T was defined as alpha times the matrix S. So alpha was R e to the I theta. So we can rewrite it in this way. And as you see here, yes, this is scalar and this is a matrix. So this scalar, and this scalar come out after it, like this. Now you see the eigenvalue of this matrix is the value of that eigenvalue is the scalar multiple of the eigenvalue of this matrix, of this much, isn't it? You multiply a scalar on a matrix, then it changes the size of the eigenvalue at that much. So -1, if -1 is not the eigenvalue of this matrix, that means e to the minus e to the 2I theta is not an eigenvalue of S inverse S star. Here we can choose a theta such that minus e to the 2I theta is not the eigenvalue of this is sigma. It's not the eigenvalue of S inverse times S star. So we can always find the theta that makes that's not the eigenvalue, because this is a finite, this is a matrix of the size n by n. So it has only n eigenvalues. But we have infinitely many thetas. So we can always find the value that makes not same as that particular n eigenvalues. So they're existing. So we can always choose. We can choose alpha. So that makes T is non-singular. So now we choose the theta in that purpose. Then we can construct a matrix T that T plus T star is non-singular. So A is equal to T plus T star times A star times the inverse of T plus T star. And as you know, this T plus T star is Hermitian. Okay. That's it. So that part is done. A is similar to some matrix H, like this. It's a non-singular matrix, so it's similar, like this. Okay, with the Hermitian matrix. Okay, next. C implies D. What was C? C was the A can be written as H A star H inverse for some Hermitian H. Now we show A can be written as HK, and H and K is are Hermitian, and one of them is non-singular. Okay, let's prove it. Let K be A star H inverse. A star H inverse. Let's write it as a K just. Okay? Then now A is same as this. This is same. The HK. Now we show. We know the H is Hermitian. All you have to show is this K is Hermitian. And one of them is non-singular. This is non-singular because H is here, H inverse is here. This is non-singular already. So all you have to do is just to show K is Hermitian. Isn't it? From here to here. So show K is Hermitian. K star is what? K is H star H inverse. So star here. So it can be written H inverse star times A. But H is Hermitian, so it's same as itself. So H inverse A. But this is same as H inverse A. What was A? What was A? A was what? HK, isn't it? So this gone. So this it's just K. So K star is same as K. Okay? Done. So this is a Hermitian. K is Hermitian. Okay, D implies it. Here D is H is a product of two Hermitian matrix and one is non-singular. And E is what? E is just A is a product of two Hermitian matrices. So this implies this one. Okay, no problem. Done. Last, E implies A. If A can be written as the product of two Hermitian matrices, we have to show A. That means A is similar to a real matrix. Okay? This is the only part. Okay. Actually, the others are all easy. This is a real part. Okay. Now we divide it as two cases. One case, this H and K's are one of these two are non-singular, and case two, and both are singular. Okay, we divide as two cases. One of them is non-singular, or both are singular. Okay, not both singular means one of them is non-singular. Okay, there are only two cases that we can think. For this case one, we show E implies B. Then directly, since we know A and B are equivalent, we can just reach to B. And for this case, we show from here to A directly. That's our strategy. Okay, start. If H is non-singular, then we show A is similar to a real matrix B. Okay. So H inverse AH can be written as, since A is HK, let make it some, okay, yeah, A is HK, we can just replace A as HK. Then H and H inverse are gone. So we have KH. But K and H are both what? Hermitian. So it's same as K star and H star. Okay? So we can write it as a HK star, conjugate transpose of H times K. But HK was A. So it's a A star. What that means is A is similar to A star, which was part B. A is similar to H star. Then we know H is similar to a real matrix B. It is part A. It's done. So that case is just done without any problem. Okay. Next. Both are singular. If now we have A is equal to HK, we want to show H is similar to a real matrix B. Now we have this is both are singular. Okay, let's start. Let's start with the H singular matrix A. Now H is a singular matrix as well as K. So we now use mass induction on N. Which the mass induction on N. When N is equal to 1, it's just trivial. It's 1 by 1 matrix. Yeah. Then it's done. It's a singular 1 by 1 singular matrix. What that means? It's a zero matrix, isn't it? 1 by 1 singular matrix. If it's non-singular, if this is not 1, then it's not a non-singular matrix. Okay. Now assume true for all L less than N. Now we show the statement is true for all N. Okay, there exists a unitary matrix U. There exists a unitary matrix U such that U star HU is the same as the direct sum of matrix D and zero matrix. where D is a non-singular matrix with real diagonal entries, and K is less than N. So it's a rank K matrix. Okay? Rank of D is equal to K, and it's a non-singular real diagonal matrix. Okay? There exists a unitary matrix. Okay, now we start. This is same. This is same. And so we can do the D is a matrix like this, and this matrix, the U star H is D times these are zeros and zero matrix like this. Okay, we don't need this K here. We don't need this K. This just shows the size of it. Okay. Anyway, so U star HD is same as this. Okay, and U star KU, we can write it in this way. Same size. We don't know what it is. But these are all zeros. So if we multiply it, so H prime U star KU is same as so H prime. This is H prime. So this is H prime. H prime U star KU is same as this times this, and here U star is a unitary matrix. So this is gone. So this is same as U star HKU. HK is A. So this is U star AU. And this is this can be written this way similarly. And this is same as this, and this can be written as a block matrix like this. K prime is there. Then the product of two matrices, product of these two block matrices, dk prime is here, and 0 times k is 0, and 0 times k star is 0, so this is 0, and 0 times star is 0 times star is 0, 0 times star is 0, so this was 0. We don't know what it is, but this is the block matrix of that we have. Now this is this. This is this. Isn't it? They are same. So, okay, so now think about this K prime. This K prime is the principles of matrix of Hermitian matrix K. K and H were both Hermitian. They were both Hermitian. So this K prime is the principles of matrix of Hermitian matrix. So this dk prime is what? It's a product of two Hermitian matrices. D is a Hermitian matrix. D is because it's a non-singular real diagonal matrix, and K prime is also the Hermitian matrix. So this dk prime is the product of two Hermitian matrices. Furthermore, D is non-singular. D is non-singular. That's what we define. Okay. So now, and K is strictly less than N. Now we can use mass induction. Use induction hypothesis. Now we use induction hypothesis because we have a Hermitian product of two Hermitian matrix with a smaller size. Then dk prime is similar to a real matrix B of size K. Now we think J be a Jordan canonical form of B. J be a Jordan canonical form of this real matrix B. Then U star AU is similar. U star AU is this one, but since the Jordan canonical form of B is J, so this block matrix is similar to this block matrix. So, but as we found it, so this matrix dk prime is similar to this matrix. Now we let this block matrix as C, then we have U star AU is similar to C, which says A is similar to C. Okay. This implies the power of A minus lambda I is similar to C minus lambda I for every positive integers, which says the length of those powers are same, and that this length is, because it's a Jordan canonical form, this gives us this equality from the knowledge that we have on the Jordan canonical form. Then what it gives? Then we have the Jordan block of A corresponding non-zero lambda is same as Jordan block of J, which is a Jordan block for the real matrix C. So the Jordan block of C is similar to a non-real eigenvalues that appears in a conjugate pair, complex conjugate. So the Jordan block is similar to a matrix with every non-real eigenvalues appeared as a conjugate, complex conjugate. That means the Jordan canonical form of C is similar to a real matrix. So A, we have shown the C is similar to A, but C is similar to a real matrix. So we show A is similar to, we have shown that A is similar to a real matrix B. In the case, the both are non-singular. Both are singular. So we have shown that if A can be written as a product of two Hermitian matrix, it implies A is symmetrical to a real matrix. So it shows the theorem that we have proved. So this was very interesting argument that we have used. So Hermitian matrix has a pretty much of interesting fact. Okay, there are some homework problems on page 174. 1, 2, 3, 11. 1, 2, 3, 11. Okay. Yeah, if I assign you, then I can give it to Hana and Horol, Jung, and Jin. Okay. You may try some of this problem. Okay, next. Now we think the variational characterization of eigenvalues for Hermitian matrix, section 4.2. These days, since you are interested in the combinatorics, this is very well related to the combinatorial matrix theory. So we better know. Many problems of optimization problems are using the eigenvalues of Hermitian matrix. Yeah, as you saw it before, you have found the maximum of x star ax such that something like this. And this is one of the optimization problems. You found it. this is the largest eigenvalue, isn't it? Like this. So the eigenvalues of Hermitian matrix can be characterized as a solution for many optimization problems. Let's see. Suppose A is a Hermitian matrix. Then all the eigenvalues are real. So we can give an order. Okay. So set of eigenvalues are lambda i's, and we give an order in this way. The lambda 1 is the minimum eigenvalue, and lambda n is the maximum eigenvalue. Okay. Then these smallest and largest eigenvalues of the matrix A can be characterized as the solution of constraint minimization or constraint maximization problems. Constraint maximization problems. This largest eigenvalue can be characterized as a solution of this constraint maximization problem. And this smallest eigenvalue lambda 1 can be characterized as the constraint minimization problem of this type. Now we think this x star ax over x star x. This is called Rayleigh-Ritz ratio. Rayleigh and Ritz are English physicists. Okay, now think. This is theorem of Rayleigh-Ritz. Let A be an Hermitian matrix with ordered eigenvalues, lambda 1 and lambda 1. Suppose we have n eigenvalues and it has that order. Then, with orders like this, then it's a Hermitian matrix, so all eigenvalues are real. Okay, with orders like that. Then we know all this value is bounded, or has a lower bound and upper bound with this form. This comes from field of value or the numerical range. This is the same as the set of x star ax. Okay. This is the range of A, field of value. A. This is set of it. This maximum value. The interesting thing is the maximum value is the largest eigenvalue, and minimum value is related to the smallest eigenvalue lambda 1. So these are the real number, so that should have a maximum, that has a minimum. This is this value, and this is this value. This is what Rayleigh and Ritz found. Very interesting. I will show it. Yeah. Anyway, as you see here, lambda maximum, the largest eigenvalue lambda 1, is the maximum of this Rayleigh-Ritz ratio. If we restrict it as a vector with the size 1, then it's just the value of x star ax. Okay, same thing. The minimum value of this with this condition, which can be written in this way, is the smallest eigenvalue of that matrix. Now we show why it is so. This is very important. For the Hermitian matrix, for the minimum value and maximum value, you don't have to do nothing. Just find the eigenvalue. Isn't it? Yeah. For this field of value, and this is the numerical range, when you study, you already know what's the minimum and what's the maximum. Okay. First, since A is a Hermitian matrix, there exists a unitary matrix U, such that U star AU is a diagonal matrix, say lambda 1 and lambda Okay, since it's a unitary matrix, there the we can x star ax can be written as x star. So you just replace a as u sigma and u. Yeah. Then we can rewrite it in this way. Since this is a diagonal matrix with real numbers here, this can be written. This is a vector, and this is another vector, and this is a scalar matrix with just only diagonal, real diagonal entries, and all others are zeros. So this can come out. Just add it. This is going to be a 1 by 1 scalar. The scalar times transpose of a vector times the transpose of the vector. So it will give us 1 by 1 scalar. Okay. Anyway, so so each of these entry come out, and we have the product of this vector times this one. So it's kind of inner product, which is this. We have a v u star u like this. But as you see here is the column vectors. The first, the i's column vector, and column vectors is transposing i's column vectors like this. So we have this 1 by 1. Okay. Anyway, now we have this because it's a diagonal matrix here. All the others are gone. All are left are the corresponding ones. N of them. Okay. So from here you see lambda. So think about the minimum. This is same as this, which is this. Now we have that, which is this. So from here, this is lambda i's, and these are all same. So if we choose the minimum for all of them, then you should have an inequality like this. If you choose the maximum of this one and take it off, then you should have this inequality. Okay? But think about it. What is this? This is a unitary. U is a unitary matrix. Unitary matrix. So U star x, i's component of U star x, and square of it, the norm of it, is same as this, because unitary matrix is isometric. So it preserves the length. So the length of this is same as length of vector x. And you just add it. What that means is it's the inner product of x. Isn't it? Okay, so you can rewrite it as this. And this one so same. So what do you have is this. What do you have is this. Okay? Then what's the minimum of among the eigenvalues? The very first one, lambda 1. What's the largest eigenvalue? It's lambda n. Okay? That's it. Now we have this, as well as the inequalities. Furthermore, this lambda 1 and lambda n are eigenvalues of A. So it has the corresponding eigenvectors. It has the corresponding eigenvectors. If you have x star ax, then that's the lambda 1 x star x. This means if you delete it, it has ax equal lambda 1x. Because x is non-zero vectors. It has a corresponding eigenvectors. What that means is there really exists. This is same as this. What that means is you have the vector. So actually there exists a vector x that equality hold, which we say this inequality is sharp. There is no better inequality than this. Okay? So, this inequality is sharp. That's the best inequality that you can get from here. So, if you rewrite it, then lambda 1 can be written as the minimum of this, and lambda n can be written in this way, because if we divide it, this gives us. So for the Hermitian matrix, the real eigenvalues, the smallest and largest eigenvalue, has a very important meaning. Okay? And this is the fact that was shown by Larry Leach. This is very important. As I told you, every matrix can be written as Hermitian and skew-Hermitian part. We saw most of research on a general matrix can be replaced by research on Hermitian. When we deal something, we always find the maximum and minimum value relate to the given information. Since this Hermitian matrix has real eigenvalues, we can easily find those eigenvalues, and also it's unitarily diagonalizable. This smallest and largest eigenvalue give us a lot of information on the problem. So this is a start of numerical linear algebra. We don't have to find all the problems. We just go the extreme point to find it. So from here, a whole new area of mathematics, a whole new area of linear algebra started. Okay, Rayleigh-Ritz theorem gives us informations on the largest eigenvalue and smallest eigenvalue. Okay, but what about the others? We now know lambda n and lambda 1. We now know how we can deal with the smallest and largest eigenvalue and the meaning of it. What's next? What's in between? Can you get any information out of this? What's the role of it? You can think. When we saw the Ch4 theorem, do you remember? SC, Ch4 theorem. Did you remember? When you have a block matrix, the eigenvalue structure was preserved in the block matrix. So there are some kind of relationship between those eigenvalues. Now we use those intuition to this Hermitian matrix and the order of these. Okay, here is the answer. This is the note. Now we think about what kind of information we can get on these remaining eigenvalues. Suppose lambda 1 is the smallest eigenvalue, and the u1 is the corresponding eigenvector. Then we can think other vectors u which is orthogonal to u1. Consider other vector u such that it is orthogonal to u1. It's a unitary matrix. Ch4 theorem, the Hermitian matrix is unitarily diagonalizing. Every vectors are also normal column vectors. Okay, think about it. Then we can use some information because the Hermitian matrix has many interesting informations in it. Okay, we try to consider the vector u, which is orthogonal to u1, which was also a vector corresponding to the eigenvalue lambda 1. Then, by the similar method, we can find the second smallest eigenvalue lambda 2, like this. We think the same vector and find the minimum of it, but this x2 is chosen among the vector which is orthogonal to u1. Then, as you see, this is direct sum because u is similar. U is unitary diagonalizable. This block and this block has a totally different structure. It's like a direct sum. It's diagonalizable. So you just think about also the vectors who is orthogonal to u1. Then all the others are in here. So you try every vectors that makes the smallest of this among all except those vector u1, and this is scalar multiple. Then this is same as this, and we can find the smallest scalar among them except lambda 1, and also we can show it is the eigenvalue, which is the second smallest eigenvalues. This is all from the property of Hermitian matrix. We can continue this argument to find lambda 3 and lambda 4. When you try to find lambda 3, all you have to do was deal with the vector which is orthogonal to u1 and u2. Then it has this type of structure. So we can find the one, but the vectors and eigenvalues other than lambda and lambda 2, but still it is smallest. Then we can have the lambda 3. Okay, anyway. Okay, from the Coulomb and Fisher found this theorem by using that argument. Coulomb is a very famous professor. He was a founding professor of Coulomb Institute at New York University, which gave a pretty much of good contribution to American mathematics in the early years. Johns Hopkins and Chicago, Harvard, and Princeton, and many others. But here, New York University was added as one of the research power when Coulomb was recruited by New York University and established the Coulomb Institute of Mathematics at New York University in 1930s, 40s. Okay, anyway, these are the research which was done not long ago, within 100 years, about 60, 70, 80 years, even 60, 50 years. Yeah. Okay, anyway, Coulomb. The Hermitian, if it's a Hermitian matrix, then the minimum of this, lambda w1 to wk minus 1, then you can find the case smallest eigenvalue from here. Okay. This is a maximum of this will give us the case smallest eigenvalue of A. If we start with the other direction, we start from the maximum, then use the max and min. And among the maximum and smallest, find the smallest one. Then we exclude the W1 to Wn minus k, then we can find the lambda k from the largest side to the smallest. It's very simple idea. Very simple idea. We have infinite many vectors x. So so actually we don't have to check all this minimum and maximum. This is a continuous function. But the compact domain, we know it's a closed compact domain. We know there exists a solution. Since it's a continuous function, we know these extreme values are achieved at these vertices. So we only need to worry about those critical points, those vertices, to find this minimum and maximums and all those things. These are all the start of a linear programming. You know, when linear programming started during the Second World War study, these were the basic research to support all those. Linear programming is the one that if we have the constraints like this, then there is a solution in this domain. But you don't have to worry about any of these, because the solution will come out from one of these. So you have to check only these. You can have many of these points, but you don't have to check all these extreme points. You just start with one point and go to the vertex which has a better solution, better chances. Then you, after a couple of the checking process, you will end up to the optimal solution. And this is just the tedious, this kind of routine process. So, computer that von Neumann developed can be well used to give us the solution. These are all the theories that support the progress of those research, finding the optimal solution. Okay, here I will give you some problems. The problem, page 181. I will give you 2, 3, and 4. This time I will give you, I will assign homework to Jin here and Horol here, and who's going to do number 4? Hana or Jung? Volunteer. Who's going to do? Okay. Okay, I will assign only 3 homeworks. Okay, next. Some applications of the variational characterizations. Variational characterizations. Why gave this theorem? All of these were developed in 20th century. This is a fairly new theorems. All those mathematicians are that we lived together, even with you. They lived when you were born. They are not the old mathematicians that you never had a chance to live together. Okay, here anyway. The A and B are Hermitian. Then we can you know, these are the ordered eigenvalues in that order. It's Hermitian. Then the case eigenvalue of A plus B is bigger than the case eigenvalue of A plus the smallest eigenvalue of B. And this is smaller than equal to the case eigenvalue of A plus the largest eigenvalue of B. this is the kind of problem that everybody are curious, isn't it? What's the eigenvalue structure? This fact made the whole change of different. This made when Arthur Cayley found this fact, that just opened the whole new area of mathematics. The important thing is do the same thing on the each one of them. Compare to the effect of the same function after the operation of those two. This is the same thing. What's the eigenvalue structure of A plus B compared to the eigenvalue structure of each one of them? Isn't it? If you find something, then it will make a whole new area to do of work. So this must be a very interesting problem when we started it. But we can only compare the size of two numbers for the real numbers in general. Hermitian matrix X has the eigenvalues, all reals, with the order. So that's a very good subject you consider. Okay, we know this. We know the this Rayleigh-Rich ratio is in between the smallest and largest eigenvalues of B. So we think about this. The Rayleigh-Rich ratio of A plus B. Yeah. From the Coulomb-Fisher theorem, we know the case eigenvalue of A plus B can be written in this way. Okay, and we can divide it in this way, but we know this. This one is always bigger than or equal to this very smallest one. If you replace it, always. Okay, then just we divide it, then we can have this. We can divide this one times just lambda 1 of B. This is definition of the case eigenvalue of A. So we have that. Very simple, very easy. The others are same. Yeah, the others are same. Yeah, the others, what you want to show this one, you just try to write it. It's exactly same. The other, yeah. Write the proof for lambda k of A plus B is lambda k of A plus lambda n. This is just write the proof. Trivial. Same. Okay, so we have found how important it is. Okay, if we use the theorem that we have studied. Suppose we have a special matrix B. Special matrix B, such as positive definite matrix, or rank 1 matrix, or rank K matrix, or bordering matrix. Suppose we have a special matrix B, then we can improve the theorem to get the new conclusion, the better conclusion for these both special matrices. The first one, let's try. For the positive semi-definite matrix. And you know what's the definition of positive semi-definite? And we know this is for all x, if x star dx is non-negative, then this B matrix is positive semi-definite. So AB are Hermitian, and B is positive semi-definite, then we can always have this. This is because what? Lambda k of A plus B is lambda k of A is always less than than what? Lambda k of A plus lambda 1 of B. Because, B. Always. But this is always, this is because what? B is positive semi-definite. Every eigenvalue of V is in the, every eigenvalues are non-negative. So this is non-negative. So this is true, and then this comes from the previous raised theorem. Okay, that's it. And next, interlacing theorem. Here, you should understand that this is A is a matrix, and this is a product of two vectors. But still, that's the G star Z this is what? This is n by 1, and this is 1 by n. So this is a m by n matrix of rank 1. So this is a matrix, and this is a rank 1 matrix. So now we are thinking about rank 1 matrix. Okay, here. So this is a matrix, and this is 1 by 1, the n by n rank 1 matrix. So from here, we can think about the eigenvalue of this matrix, and which also can be obtained. If this is a case eigenvalue of this one, then that's smaller than the k plus 1's eigenvalue of A, and that's smaller than the k plus 2's eigenvalue of A plus B. This is called the inner racing. The inner racing means if you have something which is in order like this, then there are something in the middle, so like this. Okay. This is improved in the way that as this theorem. This is. As you see here, like this is an interlacing theorem. True. Like this. So the eigenvalue of A is lambda 1, lambda 2. Suppose we have ordered eigenvalue of A like this. And this one, A tilde, is the n plus 1 by n plus 1 matrix. Because this is a matrix, A here, there's a vector Y, here Y transpose, Y star, and here we have A. This is a n plus 1 by n plus 1 matrix like this. So we have n plus 1 eigenvalues. Here, lambda hat 1, lambda 2 hat. We have lambda n plus 1 hat here like this. So we have n eigenvalues here, n plus 1 eigenvalues here. These two has a pretty much of interesting relations, each other. When you expand it like this, we call this is a bordered matrix. We have a border in addition to the original matrix. Very interesting thing is there are relationship between these two set of eigenvalues. How? Like this. This has one more eigenvalues over this. See the structure. The very smallest one of this is in first, and then this one, then this one, and then this one, like this. Okay, then this one and this one, in this order. Isn't it interesting? That's called interlacing. 하나가 나타나면 그 다음 게 사이사이에 끼어서 이게 이런 그 저기 커튼 같이 사이에 쫙 끼는 거 있죠? So that's why it is called the interlacing theorem. Something in the between. The proof of this one is strictly based on the previous theorem, and this is a very interesting fact. If you go to my homepage, you can find the 대학 수학 교육 site. Then there is a sample paper that you can download to use as a form, submit form. Okay. Here there is a math monthly. There is a one math monthly paper. Its sample form is a one math monthly paper about this interlacing theorems, written by Professor Seokkeun Hwang recently. You will see. Okay. So these are still very pretty much of interesting fact, which still we do study. Okay. Anyway, this is also used Coulomb-Fisher theorem, mini-max, max-mini. Okay, and before I go back here. So, okay, let's see. Here, if B is a Hermitian matrix, then B is a unitary diagonalizable. So rank of B is same as the number of non-zero eigenvalues of B. Let's say it's R. Okay, let's say the rank of B is R. Then U, this B can be written as beta I times U to the i's column times U to the conjugate transpose of U to the i's column. Then this is a 1 by 1 matrix times the scalars beta i's. B can be written rank K matrix. If it's Hermitian, there is a unitary diagonalizable. If it is unitary diagonalizable, B can be written as the linear combination of rank 1 matrices. You understand? This is a linear combination of R rank 1 matrices. Suppose you have a Hermitian matrix with rank R. Then your study on this Hermitian matrix is only a study of rank 1 matrices. If you know about the rank 1 matrix, then you can have all the information for the given matrix. Isn't that interesting? Rank 1 matrix is just this times this n times this. This is rank 1. All the columns are linear combination of one vector. So all the information here is like a vector. So you know everything almost. You know almost everything on this rank 1 matrix. You have R of them to make this matrix B. So for the Hermitian matrix, you can change the problem to a very simple problem. And if you draw the information from those rank 1 matrices, then you can supply all the information for the Hermitian matrix. So this Hermitian matrix is really, really important. Hana, do you agree? So the many problems, we don't have to study all arbitrary matrix. We only study the Hermitian part of the matrix. Hermitian matrix is unitary diagonalizable, and everything can be, theoretically it can be. But the many problems related to that Hermitian matrix, particularly optimization problems, linear programming problems, those are only require the information, the eigenvalues, which are all layers, which has the orders. Extreme values are appeared on the minimum and maximum. For the first one, you can easily find it. But not only with that. We can also find the second largest one, the second smallest one, and the third and fourth, etc. So we can find all the information without much difficulties. And also, as you see here, any arbitrary Hermitian matrix of rank R can be written as a linear combination of rank 1 matrices. That's the key. And also they gave us the interesting eigenvalue problem for both of matrix, which was this. Isn't it interesting? These eigenvalues are appeared in these orders. These are all comes from Fisher theorem and Lee theorem, etc. Which was lived and contributed a lot in 20th century mathematics. Okay. Here, theorem 4.3.10. If we have this structure and let lambda be a diagonal matrix, let this the sigma as a lambda 1 to lambda. Let's say this is an diagonal matrix. Then there exists a real number alpha and real vector y such that A hat has this, and this matrix has these eigenvalues. Lambda 1 hat, lambda 2 hat, and lambda n plus 1 hat as the eigenvalues. We can always develop this matrix. So this is information for the inner-racing eigenvalue problem for the bordered matrix. So we can expand to a larger number, or we can construct a matrix with the information that we like to give. Okay. Next. Inclusion principle. Here, let A be a Hermitian matrix. Hermitian matrix, and A R is the R by R principles of matrix of A. Lambda K of A has satisfies these inequalities. Here, this is a principal submatrix of A. The case eigenvalue of that principal submatrix of A has a relationship with the eigenvalues of the original one. Okay. This is called the inclusion principle. So even with the sub-principal submatrix of A, the submatrix also have some relationship with the original matrix in the sense of eigenvalue. And this is the next corollary is called the Poincaré separation theorem. Poincaré separation theorem. Great French mathematician. And this kind of the information is very useful when we have some information about this matrix. This kind of the theorems can be used in quantum physics, quantum dynamics. These are the researches that was done during the Second World War. Einstein did it, and Veblen, Oswald Veblen did it. And these are the things that the American mathematicians started over European mathematicians who had a long history of mathematics. Okay. So when you have some information, then we can use those facts to draw the next conclusions. Let's start with the n by n matrix A, and let's say these ui's are also normal vectors. Let's say BR is a R by R matrix. Okay. These are the vectors. These are the vectors. These are the vectors. Each columns are each entries are. These are the vectors. These are also normal vectors, and this is the ijth entry of this BR matrix. Okay. Okay. These are the vectors, and these are G as elements. Okay. Then this BR matrix, the case eigenvalue of this matrix is this. Particularly, it's also normal vectors. This gives us more information because we know exactly what's the entry of the matrix which is generated from the given matrix A. And this kind of theorem has been used in the physics. For the above BR, there exists a unitary matrix U with R orthonormal columns. Not the unitary matrix. It's a rectangular matrix with R orthonormal columns. When n is equal to R, it's going to be a unitary matrix. There's a matrix U with n R orthonormal columns such that BR is a U star A U. These are all the consequence of the information that we found. So when they started this research, many papers comes out from these areas over the years. Trace of BR is a trace of the summation of the eigenvalues, and when it's a Hermitian, the summation of the R eigenvalues are the minimum of trace of U star A U, and here from the smallest one to the rth one, and this is the backward, the R of them. This is a maximum of trace of U star A U, and the next theorem is about the subspace of K dimension. When A is a Hermitian and SK is a subspace of K of dimension K in Cn, of dimension K in Cn, then there exists a constant C2 such that x star Ax is greater than or equal to C2 x star X. Then eigenvalue has this kind of order. Compare the inequality is a very important subject on the research of mathematics. Here, this gives us the inequalities. And also, if there exists a C1 such that x star Ax is less than or equal to C1 x star X, then we have this order. Okay. These are all comes from the arguments that was developed. And so, in the textbook, here's the proof. A similar thing. Here's one more corollary. The proof of all these are pretty much of straightforward. Just follow the definition and compare it, because it's all related to the direct sum of it, because it's also normal vectors and distinct eigenvalues. So you can always think without much difficulties when we think the orthogonal vectors like this. The next color is about when you have a Hermitian matrix, then A has at least k non-negative eigenvalues. If we have a strict inequality like this, if it's a non-negative like this, then you have a non-negative eigenvalues. If you have a strictly eigenvalues, strictly the numerical value range, which is non-negative, then you have positive eigenvalues. If you have a k, if you found a k dimensional subspace that's satisfied with this one, then you can say that you have at least k positive eigenvalues. So this is just all the information of this has give us a lot of information on the eigenvalues. So there is a field of study, which is a set of field, we call it a numerical range, or field of value. If you go to the Math Science Classification 2000, then you will find area of research in this. This is a very popular research area in numerical linear algebra, which is widely used in the application of matrix theory. Okay, next. The proofs are that very much straightforward, as you can just read it. Here, the next one is main concept. The main diagonal entries and the eigenvalues has a very interesting relationship, which is called majorization. So eigenvalues and diagonal entries. You have a matrix A here, A11, ANN here. You have a diagonal. You have a diagonal matrix, which is an eigenvalue. Suppose you have similar, A is similar to this diagonal matrix. What kind of relationship between this and this sequence of numbers has? Any relation between these numbers and these numbers, AI's and lambda i's? What's the relationship between these two sequence of numbers? This was answered by the concept of majorization. The next section is about the majorization. There are two ways of defining the majorization. Usually the best reference for the majorization is written by Olkin and but this book, the matrix analysis book, had a better definition of it. But the book matrix, the majorization and its inequalities, and that's the one whole textbook like this volume. Yeah, I will show it later. And now I introduce the concept of majorization. Okay. the precise relationship between the main diagonal element and the eigenvalues are given by the notion of majorization. The definition of majorization is like this. So we have two vectors, alpha and beta. Alpha is majorized by beta if it satisfies this condition. For all case, and equality holds at the end. If we order the vector in increasing order, so I mean this way, if we give an order on the eigenvalues and the diagonal entries, then we can find some kind of reordering like this. Then what this means is this. Alpha is majorized by beta, if and only if summation of, so A11, for example, is better than beta 11, alpha 1. Alpha 11 plus alpha 22, for example, is beta 11 plus beta 22. You know what I mean? Alpha 11 plus alpha nn equal is beta 11 plus beta nn. But as you see, at the end is equality, like this. You know what I mean? It has, the first one is less than or equal to the first one of the other one. The addition of first two still has the same inequality. Addition of first three has the same inequality. Addition of first four has the same inequality. But at the end, the summations are same. Then we call the first vector is measured by the second vector. This is the definition of majorization. It has a whole lot of work to do on this. I wrote a paper on the majorization preserver when I taught this to one of my graduate students. We were able to adopt this concept for the preserver problem, linear preserver problem that I have worked on. So we started to publish one paper, but at the end of publishing a lot more papers, more than four papers on the majorization problem preservers. Also, that became to the problem of Professor Ando, Hiai, and many others. In the general form of the last and final paper that we finished was on this area, was matrix majorization problem in a very general sense. Anyway, I will talk about the majorization. Since time is almost up, so I will end here, and we will continue on the majorization and its application next class. Any questions? Any questions? For all?